Here I am going to explain the datasheet of mu A741 general purpose operational amplifiers. So basically mu A, that is the company name that Fairchild Semiconductor that designed the IC. If it is a national semiconductor, starting series is LM. 7 stands for there are total 8 pins in this IC. It is a DIP package, dual-in package. 4 pins on one side and remaining 4 pins on other side. So 7 first number indicates out of 8 pins, 7 pins are active pins. 4 pin out of 4 pins, that 2 pins are input pin and 2 pins for the power supplies, and 1 pin that is not used. So 741 indication 7 is total 7 pins are active pin out of 8 pin. 4 pin that is for input and output purpose as well as power supply, and 1 pin that is not connected. So in the data sheet we have a different manufacturer parameters mentioned. So MUF741C, that large C indicates there is a commercial temperature range 0 to 70 degrees centigrade. In the data sheet we can also find out the pin diagram of the IC. So as I said that there is a DIP package, dual-in package. One side we have a 4 pin and on other side we have a remaining 4 pins. So pin number 1 in the pin diagram we have a offset setting. So this offset setting is used whenever we want to remove the output voltage without any input voltage. So at that time we have to adjust the offset as a 0 value. So for that purpose we have a pin number 1 as well as pin number 5. Pin number 2, that is for inverting input. Pin number 3, that is the non-inverting input. Pin number 4, that is the power supply VCC plus 15 volt. Pin number 6, that is the output of IC. Pin number 7, that is the plus 15 volt, and pin number 4, that is minus 15 volt, and pin number 8 is not connected. So out of these 8 pins, 7 pins are effectively used. Now in the data sheet we have a electrical characteristics as well as switching characteristics. So in the electrical characteristics, very first parameter you can find as a offset parameters. So we have a input offset voltage that is mentioned in the data sheet for the 741 series IC. Input offset voltage maximum is 6 millivolt. The second parameter is input offset current that is mentioned in the IC as a 200. Input offset current that is mentioned in the IC as a 200 nanoampere. Third parameter in the datasheet mentioned as a input bias current, that value for 741 is 500 nanoampere. The input resistance between inverting and non-inverting terminal is mentioned as a 2 mega ohms, as well as very important parameter as for the noise performance, that is the common mode rejection ratio CMRR. So for 741 IC this value is mentioned as a 90 dB. So if the more the CMRR, we have a better matching of the input and input terminals. So detailed demonstration of these all parameters we will see in the laboratory. In the same electrical characteristics we have a supply voltage rejections, we have maximum output voltage swing. These are all other parameters are also mentioned in the data sheet. In the switching characteristics, important parameters we have a slew rate. So slew rate, that is the maximum rate of change of output voltage with respect to time, and for IC741 this value is 0.5 volt per microsecond. So these all parameters we are going to demonstrate in the laboratory one by one, and practically we will understand the importance of these parameters. Then after we will see the application of this IC741. This is the first parameter as an input offset voltage for IC741. Here first we are going to measure the Vout. That Vout we are going to divide with the gain of the amplifier that act as an input offset voltage. So feedback resistor 1 mega ohms is connected, and plus 12 volt at the pin number 7 by external power supply, and minus 12 volt at pin number 4 is connected. So there is a use of 2 multimeter, one at pin number 6 and second multimeter at pin number 4, at pin number 2. So same circuit is connected on the breadboard with a resistor 1 mega ohms as well as 100 kilo ohms in the feedback loop. So first multimeter at pin number 6 measure the value of output voltage, that is 81.6 millivolt, because multimeter is in 200 millivolt range. That value we divide with the gain of amplifier, that is the 1 mega ohms divided by 100 kilo ohms, that is 10. So at pin number 2 we can see the input offset voltage, that is 2.8 millivolt. Maximum value from data sheet is 6 millivolt. So by using this method we can measure the input offset voltage for given operational amplifier. So this we can compare with the datasheet value. Second parameter is input bias current. So if you know the input bias current, we can take the difference that acts as the input offset current. So we measure the voltage at pin number 2 and pin number 3, and then we divide with 100 kilo ohms resistor. The circuit is connected on the breadboard with external power supply and 2 resistors. This is the voltage available at pin number 7 as well as pin number 4 as a plus 12 and minus 12 volt. Now we measure the voltage at pin number 2, that is minus 0.01 millivolt, and at pin number 3, that is at the non-inverting terminal, is minus 3.0 millivolt. So both voltage we divide with the 100 kilo ohms resistor that act as a IB1 and IB2, and then we take the difference of these two currents that act as an input offset current. The next parameter, that is parameter number 3, act as input resistance for 741 IC. So here the method is like this. First we keep the external resistance Rx as 0 and we apply some input voltage at non-inverting terminal and we see the output voltage. Then we set the external resistance in such a way that output voltage becomes the half, so that Rx act as an input resistor. So here we apply some input voltage from DC power supply at pin number 3 at the non-inverting terminal as a 0.4 volt as external voltage, and at present the value of decay resistance box is 0. So we measure the some output voltage as a 0.9 volt. Now we set Rx in such a way that the output voltage at pin number 6 becomes the half the original value. So we now increase the value of Rx in such a way that the point at which this value becomes half act as an input resistor. So 100 kilo ohms, 200 kilo ohms, generally the input resistance is the larger value. So in terms of data sheet it measures as a 1 mega ohms. So practically we have to check this value. Here the decayed resistance box or variable resistor is connected at the output terminal and input is applied at pin number 3. So set the output resistance at maximum value and we decrease the value of output resistance in such a way that output voltage becomes half. So circuit is connected in the breadboard, the variable resistor is connected at the output terminals and multimeter measures the output voltage. So when Rx is maximum, output voltage is 10.6971 on the multimeter. Now we decrease the value of that 1 kilo ohms Rx resistor in such a way that this value becomes half. So that value of Rx acts as a output resistance. Generally the output resistance value is smaller value for IC 741. So as we decrease the value of Rx, we set at output voltage at 5 volt. So measure the value of this Rx that acts as a output resistance for IC 741. Generally this value practically is 200 ohms. Next parameter is common mode rejection ratio, that is the ratio of differential gain divided by the common mode gain. So we have two circuits. In first circuit we apply the different input voltage. In second circuit we apply the common input voltage. Then we take the ratio of output voltage by input voltage, that is the gain value. Circuit is connected on the breadboard. For the first circuit, two different input voltage are given as a 0.429 volt as well as 0.528 volt. So difference voltage is available, that is amplified by the gain of the amplifier. So at the output of first circuit we measure as a 1.004 volt. So difference in input voltage is amplified by this differential mode configurations, and then we measure the ratio of output voltage by input voltage, differential voltage, that is the gain. Now for second circuit we apply the common input voltage at inverting and non-inverting terminal as a 0.5 volt from the external power supply. Circuit is connected on the breadboard as shown in figure, and internal output voltage we measure this 0.539 acts as our input voltage to the circuit as a common input, and the output voltage we can see on multimeter as 17.7 millivolt. So common input volt capacity of the OPAMP is very small, so output voltage is very small, and then we take the ratio of differential gain divided by the common mode gain that acts as a CMRR for IC741. Next parameter, that is the transfer characteristics to measure the open loop gain of OPAMP. So here we are not connecting any feedback elements. We apply the input sine wave from function generator at inverting terminal, and we observe the output signal in XY mode as a transfer characteristics. Circuit is implemented on breadboard with the plus or minus 12 volt as a power supply on pin number 7 and 4, and input is applied from the function generator at inverting terminal. The nature of the signal is sine wave. Same signal is also connected with the oscilloscope, and this oscilloscope in the dual-in mode, that is the two outputs you can see at the same time. One channel acts as the input signal and second channel acts as the output. So 1 volt is the input signal, so definitely OPAMP enters into the saturation, so output is clip waveforms, as you can see as a square waveform, and it is inverting mode. If you see the output in XY mode, we can observe the transfer characteristics, that is changing V in versus changing VO. So if you want to measure the open loop gain, we have to measure the slope of these two lines. So that acts as an open loop gain, that is change in output voltage with respect to change in input voltage. Otherwise, we require the input signal which is very small, around about 120 microvolt, that act as an input signal. So it is very difficult to obtain that 120 microvolt input signal from the function generator. So we apply the 1 volt as an input signal, and then we see the transfer curve, and from transfer curve we can measure the open loop gain by taking the slope of that transfer curve. So this is the circuit setup for measuring the open loop gain of operational amplifier. Next parameter is gain bandwidth product. Here we have two circuits. For one circuit gain is unity, and for second circuit gain is 10. That is RF by R1 ratio. So same circuit is implemented on breadboard, as you can see, with the plus or minus 12 volt at pin number 7 and 4. The input to the circuit we are applying from the function generator with the constant voltage and variable frequency. So here in this experiment we keep the input voltage constant and we change the frequency of the input signal. So as you can see, both outputs and input are same at the same level. As we increase the frequency, and we have to note down the point at which gain starts to decrease. So that decreasing point is identification of bandwidth, and then we multiply the bandwidth with the gain, that identification of gain bandwidth product. So now we increase the frequency from function generator, as you can see the effect on the output signal. So you have to note down the point after which your output signal starts to reduce. So that point is the bandwidth of the amplifier. So at present gain is unity, so initially gain remains 1, but after some frequency gain starts to reduce. So that point is identification of bandwidth for the amplifier. So you have to repeat for this for multiple values of the frequency, start from 10 kHz, 20 kHz, 30 kHz, like that. Generally the gain bandwidth product is the larger number for the IC741. Now same we have to apply for the second circuit where gain is 10. So initially if you apply the input signal from function generator, gain is 10, and after some frequency gain starts to decrease. So circuit is implemented on breadboard, as you can see. So now we apply the input signal from function generator, we keep the voltage constant and we increase the frequency. So if the gain is more than 1, it means the bandwidth value we get the smaller number to keep the gain bandwidth product constant. So initially gain is 10, after some frequency the gain starts to fall. That point is the identification of bandwidth of amplifier. So if gain is larger, we can observe bandwidth is smaller, that is the circuit number 2, and in the first circuit gain is just 1 unity, so at that time we get the large value of bandwidth. So in such a way that gain bandwidth product remain constant. So here we repeat the same process. We increase the frequency of the input signal from function generator, and then we measure the point at which gain starts to fall, that is the bandwidth point. So here we apply the input signal from the function generator and we measure the output for unity gain amplifier. So same circuit is implemented on the breadboard, as you can see, with the power supply. So input signal is applied as a pulse signal from the function generator and output is observed on the oscilloscope. So we have to apply the frequency at which output is look like distorted. So that is a maximum signal frequency you can apply from the function generator. And then you have to measure the slope of output voltage with respect to time. So that value is the identification of the slew rate. It means we are going to see what is the rate of change of output voltage with respect to time as a slew rate. So you cannot apply 1 kHz, 2 kHz initial value. You have to apply that frequency first, for which output is look like distorted. So here you can see the circuit diagram for switchable inverting or non-inverting amplifier. So there is switch position is given either 1 or 2. So if switch is at 1 position, it means input is available only at inverting terminal, and if switch is available at pin at 2 positions, it means it is inverting and non-inverting terminal. So here first we connect the non-inverting terminal as a ground. It means switch is in position number 1. Same circuit is implemented on breadboard, as you can see, with the external power supply. The input voltage at inverting terminal is applied from external source, that is a 1 volt over here. So minus RF by R1, both resistors are same, so same input is reflected at the output at pin number 6, that we can see on the multimeter as a this value minus 0.9. So this is all about for switch number 1 positions, where non-inverting terminal is ground and it's act as an inverting amplifier. Now switch is connected at position number 2, so input is available at inverting and non-inverting amplifier. Same circuit is implemented on breadboard, as you can see, and external power supply and the source as a 1 volt. So minus 2 plus 1, that is the gain formula as output voltage. So on multimeter you can see the 1 volt as the output voltage, that is minus 1 plus 2 volt. So this is all about for this part, where both switchable inverting and non-inverting configuration is possible. This is the second part of experiment as an inverting amplifier for adjustable gain or variable gain amplifier. Here you can see as 1 kilo ohms resistor is variable at non-inverting terminal. If value of this resistor is 0, circuit acts as a inverting configuration, and with a maximum value it acts as a inverting plus non-inverting configurations. Same circuit is implemented on breadboard, as you can see, with variable resistor and external resistors. The power supply is provided from external power supply, and 1 kilo ohms resistor is connected as a variable resistor. So as you can see, with plus or minus 12 volt is applied, and the input voltage is 1 volt, 0.9 volt. Now we can see the value of output voltage by keeping the resistor at the 0 positions. So circuit is inverting configurations because non-inverting terminal is ground. So you can see minus 1 volt as output voltage, that is minus RF by R1. Now if you change the value of potentiometer as a maximum value 1 kilo ohms, circuit acts as a inverting and non-inverting configuration. By changing the value of potentiometer, we can change the value of gain from minus 1 to 0. So when potentiometer is at maximum position, circuit acts as a inverting plus non-inverting configuration. So total combined gain from the equations we can find as a 0. So output voltage you can see on multimeter as a 0 value for the maximum value of potentiometer. So next experiment for the summing amplifier in inverting mode. As you can see the circuit diagram where all three resistors are connected at the inverting terminals with the VA, VB and VC as input signal. Output is available at pin number 6 and non-inverting terminal is connected with ground. Same circuit is implemented on breadboard with external power supply, as you can see, plus 12 volt and minus 12 volt. The three inputs are available as a 1 volt as a VA, VB and VC from external source. So with the same value of the resistor, we can see output voltage is the summation of all three input. So that we can see on the multimeter at pin number 6. So as you can see in the diagram, multimeter is connected at pin number 6 and the output is the addition of all three signals, that is the minus 3.11 volt. Negative sign, it means inputs are available at inverting terminal. Now we change any one of the input. As you can see the effect on output voltage. So if the input voltage is increased, addition is increased, as you can see. So you have to note down by multiple values on the observation tables what is the effect of inputs on the output signal. So addition is increased or decreased depends on the input signal. So minus RA bar that we have set as 1 ratio. So output is the minus VA plus B plus VC. So this way we can implement the summing amplifier in inverting mode. Next part of this experiment, we have summing amplifier with non-inverting configuration, where you can see that all inputs are connected at non-inverting terminal, that is VA, VB and VC. Inverting terminal is connected with ground. Output is available at pin number 6. So you can see that by mathematical formula we have to set the ratio of 1 plus RF by R1 as a 3 in such a way that RF by R1 is equal to 2. So RF is 2 times R1. So if you select R1 as a 1 kilo ohms, RF is 2 kilo ohms. So by performing the addition operations, we have to set this value of resistor, that is VA equal to VA plus VB plus VC. The circuit is implemented on breadboard by selecting proper value of the resistor, as you can see, with the choice of 1 kilo ohms and 2 kilo ohms. Other resistors are same as a 1 kilo ohms. So circuit is implemented on breadboard with additional resistors, as you can see. Output is available at pin number 6. Power supply is provided plus 12 and minus 12 volt. Three inputs are available as a VA, VB and VC, as you can see by the external power supply. Output we are connecting on pin number 6 with the multimeter. So as all values are 1 volt as a VA, VB and VC, you can see the addition as a 3 volt on the multimeter. But this value is positive, it means that inputs are available at non-inverting configurations. Now we change the value of any one power supply, either increase or decrease. The effect we can see on the multimeter. So 1 volt, 2 volt, as you can see the effect is available or addition is increased on the multimeter. Same you have to note down in your observation table by changing the value of input source. So this way we can perform the summing amplifier in the non-inverting configuration, as you can see. So at 2.8 volt addition is 2.8 plus 1 plus 1, as remaining power supply are constant. Configuration is a differential amplifier, that is the output is the difference of two input signals, that is VB and VA. So circuit is available, as you can see. Inputs are available at inverting and non-inverting terminal. Output is at pin number 6. So by mathematical formula you have to set the value of RF as R1 and R2 as R3. So by minus RF by R1 VA plus 1 plus RF by R1, we can find out the difference, that is VB minus VA. So by proper selecting the value, we can connect the circuit on breadboard, as you can see. Output is available at pin number 6. Power supply is provided from plus or minus 12 volt. So output is the difference of two input signal as a 1 volt minus 1 volt. So you can see the output voltage at pin number 6 by the multimeter, that is almost 0.11. So if you require the difference is positive, we have to increase the value of VB, or if you require the difference is negative, we have to increase the value of VB. So based on this increment or decrement in one of the supply voltage, we will get the value of either positive or negative. So by changing any one power supply, we can make difference either positive and negative. So this way we can see the differential amplifier in subtractor circuits. This is the experiment number 4 as an instrumentation amplifier. So in this experiment we are going to change any one arm of the bridge and maybe measure the sensitivity of the bridge by instrumentation amplifier. So at input side resistive bridge is connected, and next to op-amp, that is the buffer that provides the high input impedance, and third op-amp that acts as a differential amplifier. Mathematically we can see when bridge is balanced that the both voltage VB and VA are same. So we can obtain the balanced bridge condition as RC by RB equal to RT by RA. So this is identification of balanced bridge condition, and at that time output voltage is 0. So whenever bridge is unbalanced, VA and VB both voltage are different. So bridge unbalanced we can change by changing the value of resistor R. So here you can see the mathematically we can find out the bridge unbalanced condition and output voltage that is available in terms of delta R. So change in delta R that is reflected at the output terminals. So if VA is greater than VB, output voltage is positive, and VA is less than VB, output voltage is negative. That we can verify by the mathematical formula. Same circuit we can implement on the breadboard with the different value of resistor as well as the power supply plus or minus 12 volt and the 3 op-amps. Input side we have a 3 fixed resistor and 1 resistor as a variable resistor as a potentiometer. By changing this potentiometer we can change the bridge balance conditions. So at present this potentiometer is at the 1 kilo ohms, so all 4 resistors are as the same value. So in balance condition we can see output voltage is a 0.59 nearer to the 0 volt. It means bridge is balanced. The bridge is unbalanced by changing the value of potentiometer. So whenever sensor sends the signals, the resistance is changed, so that we can reflect with that we can see at the multimeter's output. So change in resistance is reflected on the multimeter value. As you can see, the third op-amp output is connected with the multimeter. So if bridge is unbalanced, change in resistance we can measure in terms of voltage. So this basically used in the instrumentation amplifier as industrial applications. So sensor signal is detected by the bridge, and whatever change in resistance value is reflected in terms of voltage. So this is practically useful for measuring the output voltage in terms of the sensors quantities. So next experiment we have a logarithmic amplifier as an op-amp application. So diode in this case is connected in feedback form, and input current emitting resistor at the non-inverting terminal. Non-inverting terminal is connected with ground. So same circuit we can implement on breadboard with some mathematical formula. So mathematically we can use the diode property current voltage relation as exponential. This we can use as a input voltage was divided by R as a op-amp current. Then we find out the input voltage in terms of the diode voltage. So by mathematical formula we can see the Vout is minus Vt ln Vin by Is into R. So same circuit we can implement on the breadboard where output voltage is available as a logarithmic of the input voltage. The power supply plus 12 and minus 12 volt is connected externally, and Vs we have a DC source voltage with the 0, 0.1, 0.2 like that. So we apply the power supply connections as well as the DC source value externally, as you can see. So at pin number 6 output of OPAMP we can see the particular value. So multimeter is connected at pin number 6 and we see the output voltage, that is the logarithmic of the input voltage. So at present it is minus 0.44 volt as output voltage for 0.1 voltage input. Now we change the VS source 0.1, 0.2, 0.3. So there is a non-linear change you observe at pin number 6. So at pin number 6 we have multimeter that gives the logarithmic value of the input voltage. So minus 0.47 for given value. Then we increase the input supply, that is 0.3, 0.4. Corresponding change you observe, but that change is very small. So there is a non-linear relation between input voltage and output voltage. So that indicates the logarithmic relations. So minus 0.53 is available at particular value of the input voltage. We change this input supply and we measure the output voltage at pin number 6, as you can see. So at present it is 1 volt and we measure the output voltage at pin number 6, as you can see, that is minus 0.55. So this way we can implement the first part and OPAMP as a logarithmic amplifier. Now in second part we have an anti-lock function. So we interchange the position of diode and resistor. So source voltage is connected directly with a diode and resistor is in the feedback path. Again non-inverting terminal is ground. So by mathematical formula we have diode exponential current voltage relations that we can use, and then we apply the KCL in such a way that we find out the output voltage in terms of input voltage. So we can, as you can see by mathematical formula, output voltage is anti-lock function of the input voltage. Same circuit is implemented on breadboard with the external power supply plus 12 volt and minus 12 volt. Input source is again DC source 0.1, 0.2 and multimeter is connected at pin number 6 to measure the output voltage. So anti-lock function is available for given value of input voltage. You change the value 0.1, 0.2. You have to note down this value in your observation table for input voltage as well as output voltage. So at 0.6, 0.7, 0.8 we can change the input voltage and corresponding linear change you observe at pin number 6. That indicates the anti-lock functionality of given circuit. So we change the value of supply voltage Vs at the input side at inverting terminal, and corresponding change we have to note down on pin number 6. So this value you have to note down in your observation table, and then you have to plot the graph of input voltage and output voltage. So that indicates the anti-lock functionality of the given circuit. So this is all about for anti-logarithmic amplifier for OPAMP application. Next experiment, we have a experiment number 6 for the OPAMP as a integrator and differentiator. So in the first part, as you can see, integrator circuit where inverting non-inverting terminal is identified as a virtual ground, so Vx equal to Vi. By applying the KCL at input side and output side, we find out the current and compare the both equation. So by comparing the equation, we find out the V out in terms of integration of input voltage. So as you can see, whatever the input voltage, the output is the integration of input is available. Hello, this is the experiment for integrated circuit using OPAMP. So there are two parts in this experiment. In one case we go for the basic circuit and second we go for the practical circuit. So in the basic integrator, as you can see, at input side we have a current limiting resistor and in feedback we have a capacitor. So it is RC combination from the integrators. But as you can see that if we apply the low input signal from the function generator, this capacitor acts as an open circuit. So in that case, the gain provided by the OPAMP is very large. So that is a practical limitations we can avoid by using connecting some extra component in this feedback element. So this circuit is same connected from the breadboard. As you can see, we connect the power supply of plus 12 and minus 12 from the external supplies. We apply the input signal from the function generator, as you can see, as a sine wave. Later on, after the integration function, we can apply triangular and square wave also. Output we are observing across the oscilloscope, as you can see. So initially we apply the input signal as a 300 Hz 0.5 volt sine wave from the function generator, and we change the frequency of signal by keeping the amplitude constant. So initially we observe that gain remain constant, and after the cutoff frequency gain starts to decrease. So now I increase the frequency from function generator. Five kilohertz, 6 kilohertz. The effect you can observe on the oscilloscope, as you can see. So see the effect of change in frequency on the oscilloscope. You have to note down the frequency where gain starts to fall. So in this all part up to 120 kilohertz gain remains constant. So this is the range somewhere 700 kilohertz where gain starts to decrease, and that you have to note down as a cutoff frequency. In this, after the cutoff frequency, if you change the signal from function generator, let's say we applied a triangular. So the integration of triangular signal is look like sine wave, as you can see. If I change the signal as a square, integration of square wave is the triangular, as you can see. So after the cutoff frequency, circuit acts as an integrator, but the limitation over here at the lower frequency gain is very high, so that you cannot limit. So for that we have to connect some feedback element along with this capacitor in such a way that we can fix the value of gain at the lower frequency. Then after, gain starts to fall at the cutoff frequency. So to avoid that limitation of higher gain at lower frequency, we need to connect some external resistor in this feedback element that acts as a feedback resistor. So that resistor by input resistor that decides the gain of the amplifier. So this is all about for the first part of basic circuit as an integrator. Now we will see the practical circuit of integrator. Second part of this experiment, we have practical integrator circuit where resistor RF is connected in feedback in such a way that RF balance set the gain value at the low frequency. So non-inverting terminal is connected with ground, and at inverting terminal we have a function generator with the variable frequency. Same circuit is implemented on breadboard, as you can see, with the external power supply, function generator and the oscilloscope. Plus or minus 12 volt is applied at pin number 7 and 4, as you can see. The input signal, we have a function generator with the sine wave of multiple value of frequency. So in this experiment, again you have to plot the frequency response, but you have to ensure that at low frequency that capacitor is open loop, so all current is passed through feedback resistor. So RF by R1 is the gain at the low frequency. So we have to change the value of frequency from function generator, and we have to note down the value of frequency after which gain starts to fall. Initially you have to do the calculation of FA and FB frequency by given specifications. So your circuit work as an integrator only in the range of FA to FB. After that we have a gain bandwidth product value. So change the frequency from function generator as a 10 Hz, 100 Hz, 200 Hz in the gradual change. So effect you have to note down on the oscilloscope. Initially output voltage is constant, and from FA to FB gain starts to fall. So but also functionality is verified by changing the function from the function generator. So we can apply the sine wave, we can apply triangular, we can apply the square wave, and multiple output are possible. Next part of this experiment, we have a differentiator, OPAMP application as a differentiator. So this is the basic circuit where capacitor is now at the input side and feedback resistor at the output side. So by virtual ground concept, we have Vx equal to Vy equal to 0.
So by applying the KCL at the input side and output side, we mathematically find out that output voltage is a function differentiation of the input voltage, as you can see, minus R1 into CF. So same circuit is connected on breadboard with input capacitors as well as feedback resistor. Non-inverting terminal is connected with ground. Input we have to apply from the function generator. Power supply is connected with plus 12 volt as well as minus 12 volt at pin number 7 and 4. So sine wave of different value of frequency 3 Hz, 10 Hz. Gradually we change the frequency and we have to note down the output voltage on the oscilloscope. Initially in this part we have to calculate the frequency range FA or FE by the mathematical formula. So now we change the frequency and we see the effect of change in frequency on the oscilloscope. So initially frequency is increased, output voltage is also increased because it is a high pass filter. So at one particular frequency gain starts to become constant, but in the very basic circuits we have limitations. We continuously get the value of input frequency for which output is increased. So the value of gain we can limit it by connecting external resistor, and also at the input side we have limitation of input impedance. Multiple functions are possible by applying a triangular as well as square wave. So differentiation of triangulars as well as square wave we can observe on the oscilloscope. Now the actual part of this circuit is a practical circuits that we are going to see. So this is all about basic circuits as a differentiator. So this is practical differentiator where feedback elements are added, as you can see, and also input resistor R1 is added to provide the input impedance for the OPAMP. So feedback we can achieve by additional capacitors, and the input impedance we achieve by additional resistor. Same circuit is implemented on breadboard, as you can see, with the external power supply plus or minus 12 volt, and input signal we apply from the function generator. So basic advantages of this circuit, we get some range of FA and FB for which circuit act as a differentiator, after which gain remain constant. Output we have to observe on the oscilloscope by changing the value of frequency. So we start with the small value of 1 Hz, 10 Hz, 20 Hz, 30 Hz, like that. Corresponding we have to note down the output voltage on the oscilloscope. So you can see the functionality of the circuit by changing the value of function generator frequency. So initially output voltage is increased as input signal frequency is increased, and we can plot the frequency response also, as you can see, by input signal frequency on x-axis and output voltage or gain on the y-axis. So by doing the experiment you have to find out what is the range of frequency for which circuit act as a differentiator. That is our range of FA and FB calculation. Gain we can find out by minus RF by Rin, as you can see on the frequency response. We have to also apply the different signal from the function generator like triangular as well as square wave. So differentiation of square wave is look like spikes, as you can see, and if you apply the triangular waveforms, differentiation of triangle is look like sine wave. So this is all about for the practical differentiator. This is the next experiment application of OPAMP for the wave shaping circuit. So in very first circuit we have a half wave rectifier where diode is connected in feedback loop. So when diode is in on state, output signal follow the input signal. When diode is off, output is 0. So we apply the sine wave at non-inverting terminal, and in feedback loop signal at inverting terminal we are comparing with the sine wave. So this diode is used whenever input signal is very small value. Still we can use this circuit for the rectification purpose. So this is a precision rectifier. Same circuit we can implement here. As you can see, diode is in feedback loop and non-inverting terminal is connected with the sine wave. So load resistor is 10 kilo ohms and inverting terminal is connected with the diode in feedback loop. So when diode is in on state, output signal follow the input signal, and diode is off, output is 0. So same circuit is on breadboard. As you can see, as diode is 1 and 4007. As you can see, power supply voltage we apply plus or minus 12 volt is available, and input signal from function generator as particular frequency and very small value less than 0.7 volt. So even with the small value and due to the higher gain of the op-amp, we can still use this circuit as a rectifier purpose. So for positive half cycle, diode is on, and for negative half cycle, diode is off. So that 0.7 limitation of normal rectifier we can avoid by using the op-amp in the rectifier circuit. So gain of the op-amp is higher, that multiply with the input signal, that is 130 millivolt. So with that output voltage, diode is in on state and output follow the input for that purpose. And for negative half cycle, diode is off, so output signal is 0. So only one cycle is available throughout the full cycle of the input, and this is a half wave rectifier or precision half wave rectifier circuit. Next we have a clipper circuit, the application of diode to remove the unwanted noise in the sine wave. So here we have positive clipper, so whatever the noise component in positive half cycle, that is removed by the diode as a clipper circuit, and during negative half cycle output follow the input. So as you can see, we apply the V reference at the inverting terminal, non-inverting terminal we have a sine wave. So when the V reference is smaller value, your diode output voltage follow the input, and otherwise it is clipped at the positive half cycle. Same circuit is available here. You can see when diode reference voltage is available with the external power supply, and input is applied with the sine wave from the function generator with the non-inverting terminal. So here we can use the positive clipper concept. Same circuit is implemented on breadboard. As you can see, diode is available in feedback loop. Output pin, that is at pin number 6, and pin number 7 and 4 we can use for the power supply, plus 12 volt and minus 12 volt. The DC source is connected also, and function generator is also available. Sine wave of 1 kHz, and this acts as our bias voltage 0.1, 0.2, 0.3. So output at pin number 6 on oscilloscope, as you can see, like this. So for positive half cycle, when reference voltage is smaller as compared to sine wave, output follow the input, diode is in on state. When reference voltage is when sine wave is more as compared to reference, diode is off, output is clipped at V reference. So in XY mode we can also observe the transfer characteristics, that input on X axis and output on Y axis. So by changing the V reference we can change the output voltage level, as you can see, 0.1, 0.2, 0.3 from the external power supply. Now for clamper circuit, application of diode as a clamper circuit, as you can see. So this is very standard circuit to follow the two step for the clamper. You have to, step number 1, you have to take that input for which diode is on and calculate V out and VC. And for second step, you have to take remaining input and find out what is the output voltage. So in first part, diode is on, so output voltage is 0. So your E in is same as VC. And in second part, diode is off, so you have to take the input plus capacitor voltage, that is the output voltage. Same circuit is available over here, that is identified as active positive clamper. So all output voltages above the 0 line is identification of positive clamper circuit. Diode is in feedback loop, and function generator and capacitors are available at the output input side. Non-inverting terminal is connected with ground. So with the step 2, you have to first take that input and we have to analyze the circuit. Same circuit on breadboard, as you can see, with the diode and capacitor. Capacitor is connected with function generator, and IC is applied with the power supply, plus or minus 12 volt. 1 kHz sine wave we apply as the input signal that we want to claim at the upper side. So output at pin number 6 we can find out on oscilloscope as a positive clamper. Entire voltage is available on above the zero line. You have to note that whenever you see the waveform, your oscilloscope in the DC mode. So for positive half cycle, output is available entirely to the above the zero line. So this is we can implement also the negative clipper by just changing the polarity of the diode. We have a negative clamper as well. So this is all about for this experiment. We have an application of diode for wave shaping circuits. Next experiment we have analog filter, that is low pass filter first order. The circuit diagram you can see as RC element at the non-inverting terminal. So by applying the mathematical formula we can find out the gain of the circuit, that is 1 plus RF by R1, as well as the cutoff frequency is 1 by 2 pi RC. So if R and C is given, we can find out what is the cutoff frequency of the filter. So initially at the low frequency gain remain constant, that is 1 plus RF by R1, and at higher frequency after cutoff frequency gain starts to fall. So this we can see in the frequency response of the low pass filter. There is the pass band as well as stop band. So initially gain is constant, then after FC 1 by 2 pi RC gain starts to fall with minus 20 dB per decay. That's why it is a first order filter. So same circuit here you can see the RF is 100K, R1 is 10K, and with the RC element is R equal to 10K and C is 0.1 microfarad. So if cutoff frequency is given, you have to select the value of C and find out value of R, that is your RC element for the filter. Here active filter because we have use of OPAMP in the circuit that provides the sufficient gain. Same circuit is implemented on breadboard, you can see with the array of RC as well as RF and R1. Input signal we have a external power supply plus 12 volt and minus 12 volt. Input signal we apply from the function generator. So here you have to obtain the frequency response with the keeping the input signal amplitude constant, and you have to change the value of input signal frequency, and corresponding effect you have to observe on the oscilloscope. So change the frequency gradually from 10 Hz, 20 Hz, 30 Hz, 40 Hz, like that, and obtain the value of output voltage on the oscilloscope. So initially gain is constant as you can see, and after the cutoff frequency, that is 1 by 2 pi RC, gain starts to fall with minus 20 dB per decay. So for the first order filter the decay is only minus 20 dB per decay. If you go for the higher order we get very sharp cutoff, that is minus 40 dB per decay. So adjust the input signal frequency accordingly. You have to note down the value of output voltage, and later on VO by V in, that is the gain, and that you have to convert in 20 log VO by V in, that is the dB value. So here we increase the frequency from function generator, and we have to note down the value of output voltage on oscilloscope. Now at the higher frequency you can see gain starts to fall. So by very accurately you have to see from after which frequency gain starts to fall practically. So that practical value is very near to the theoretical value, that is 1 by 2 pi RC. So this way we can implement the first order active low pass filter with the proper selection of R and C as well as closed loop gain of the circuit 1 plus RF by R1. So this is all about for the first part of this experiment where we implement the low pass filter. Second part of this circuit we have a second order low pass filter where we have two RC element R1 C1 as well as R2 C2. So mathematical formula is available with gain, cutoff frequency, that is again 1 by 2 pi RC if R1 C1, R2 C2 RC. So this is a Butterworth filter, so it has a proper value of gain as well as quality factor relations A equal to 3 minus 1 by Q. So delta that you have to select from the frequency response plot for the Butterworth filter. If you have a proper value of delta, we get the very sharp cutoff frequency. So here you can see different value of deltas are given 0, 0.1, 0.2, 0.5. So based on that, we can find out the value of gain as well as additional component. So same circuit available here with the cutoff frequency as well as R1, RF and the RC elements. So this filter we designed for the given value of cutoff frequency, and we find out the value of additional components, that is RF, R1 and RC element, that you can see in the circuit diagram. Same example is given in the textbook also for second order low pass butterworth filter. Output we obtain across the pin number 6. Here second order because gain is fall minus 40 dB per decay, so gain is very sharply changed as compared to the first order. So here we implement that circuit with the breadboard with the proper value of capacitors 0.0047 microfarad. So 0.001 microfarad is connected in parallel, so we get 0.005 microfarad. RF and R1 are connected at closed loop configurations. Input signal we have from function generator with the power supply at pin number 7 and 4, that is plus 12 volt and minus 12 volt. As you can see, input signal is available with the function generator sine wave of 0.5 at different value of frequency. So by applying the input signal, we have to observe the output voltage on oscilloscope at pin number 6. So here we have to obtain the frequency response. It means we have to again change the value of input signal frequency by keeping the amplitude constant. So initially 10 Hz, 20 Hz, 30 Hz, 40 Hz, 100 Hz, 200 Hz. You have to change the value of frequency, and probably at 700 to 800 Hz gain starts to fall, because we designed the cutoff frequency for 1 kHz in this example. So after 1 kHz gain starts to fall, that you have to note down in your observation table. So change the frequency and see what is the effect of this change in frequency on the output voltage. So initially we have a constant value of gain, then after with the increase in frequency, at cutoff frequency gain starts to fall. It means we are entering in the stop band. Initially the band available on frequency response is a pass band. So at higher frequency you can see output voltage, that is the first waveform, is decreased, as you can see at pin number 6. So again increase the frequency and reach up to the maximum point where gain is sufficiently smaller. So here it is 2800 Hz frequency that we apply into the function generator, and we observe the output voltage, that is the smaller value as compared to the input, that is the second waveform. So this way we can implement the second order low pass butterworth filter with the proper design parameters. So this is all about for this experiment. This is the next experiment for IC 555 timer in the A-stable configuration. So here we have to find out the change in voltage across capacitor as well as output waveforms. So we are charging as well as discharging current formula, as you can see, and the total time with the frequency of this output signal, that is 1 by T. The same time we have to find out duty cycle also for the circuits. So circuit, as you can see in the board, where we have a RA, RV and RC, these are the three external elements with the power supply of plus 5 volt. These values we have to find out for the given cutoff frequency as well as duty cycle. Output signal we have at pin number 3. So externally this capacitor is charged and discharged. Based on that we have triangular waveform across the capacitor, and during charging period we have a output is logic 1 of the square wave, and during the discharging period we have a output signal is logic 0. This we have to obtain on the oscilloscope. So 1/3 VCC to 2/3 VCC is a charging period, and 2/3 VCC to 1/3 VCC is a discharging period. Same circuit as you can see with 555 timer IC is available, So we first obtain the waveform across the capacitors, that is at 0.1 microfarad, and then later on we find out the voltage at pin number 3. Power supply is available as a plus 5 volt from the external power supply. So by connecting the oscilloscope at pin number 3, we are going to obtain the charging and discharging period of the capacitors. So output waveforms you can see at capacitor values as well as at pin number 3. So at pin number 3 we have a square waveforms, as you can see. So output is logic 1 from 1/3 VCC to 2/3 VCC, and output is logic 0, that is from 2/3 VCC to 1/3 VCC. So here for the given duty cycles we have a output signal frequency. In the experiment you have to change the value of RA multiple times, and then you have to find out the practical value of output signal frequency. This value of frequency you have to compare with the theoretical value of the frequency. So this is for the stable configurations of the 555 IC. Next part we have a monostable configurations where we require the triggering signal at pin number 2. So by applying the triggering signal, it is possible to generate the on and off period at the output terminal. So this is for monostable configuration circuits where we have to apply the triggering signal from the function generator, and we have to obtain the output signal at pin number 3. So this circuit is available with the given value of Tp equal to 1.1 Ra into C. This is the formula for the monostable configuration. So at pin number 3 we have output waveform as square waveforms, and at pin number 2 we have to apply the triggering signal, that is the pulse signal from the function generator. There's a one capacitor, that is 1 microfarad and 10 kilo ohms. This we calculated from the design formula, that is Tp equal to 1.1 Ra into C. So for given value of Tp we have to assume the value of C, and we have to calculate what is the value of Ra. Same circuit is implemented on breadboard. As you can see, at pin number 3 we have output signal, at power supply is available plus 5 volt, and function generator that is used for the triggering signal at pin number 2. So first we see the triggering signal at pin number 2 is look like this, as negative going triggering signal, and then we will see the also how the signal is look like at the capacitor. So at capacitors we have a charging and discharging, that kind of waveform is available. So during charging period what kind of waveforms are there, and during discharging period what kind of waveforms available at the capacitors. So we see the waveform at the capacitor terminal is look like the triangular waveforms. So circuit is available, as you can see now. Output or oscilloscope is connected at the capacitor point, and we see the what waveform is available at this point. So as you can see on the oscilloscope, the charging period of the capacitor and very small discharging period is available. Now we will see the waveform at pin number 3. So we remove the connection of oscilloscope from pin number from the capacitor to the pin number 3. So we are expecting the square wave at the pin number 3 when triggering signal is available. So this is useful whenever we apply any switching signal or triggering signal, we have an output waveforms. So here note down the frequency of this output signal by changing the value of Ra multiple times, and you have to compare the theoretical value of switching frequency with the practical value of switching frequency. So change the Ra and note down your observation value.
So this is the experiment for phase lock loop. As you can see, the all external components we can find out from the given specifications. So output of VCO, that is at pin number 4 or 5, that we are going to see without any input, and later on we apply the input signal and we find out what is the lock range and the capture range. So same circuit is implemented, as you can see on the breadboard over here, with the NE565 as a PLL IC with required external components. So at present we are not applying any input at pin number 2, and we have to find out what is the output, that is called the frequency of oscillation for the PLL. So that we are going to find out at pin number 4 or 5. So without any input at pin number 2, we have to see what is the reference frequency. So you can see the output on oscilloscope, and by using the proper scale of the oscilloscope, you have to find out what is the frequency of output or reference signal. So here to measure the time duration, and that you have to multiply with the divisions, and then 1 by t, that is the reference frequency. So that frequency is nearer to the 2.5 kHz as the calculated value. So now we have to find out the capture range as well as lock range. So for finding out the lock range, we have to apply the input signal at pin number 2 as a sine wave of multiple frequency, and we have to see the effect on this VCO output. So if there is a change in VCO output, it means we are in the capture range. If there is no change in the VCO output, it means we are in the lock range. So now we apply the input signal from function generator. So turn on the function generator sine wave signal with multiple frequency. So we keep the input signal frequency very small at initially. As you can see, it is 3 Hz 1 volt sine wave. So at this frequency, you can see the output of VCO on the oscilloscope. If there is a fluctuation in the output of oscilloscope, it means we are in the capturing range. If the output of oscilloscope is steady, it means we are in the lock range. So you have to find out from which frequency to which frequency output is steady. It means it is lock range, and from which frequency to which frequency output is changed. So now we change the frequency 3 Hz, 7 Hz, and in fact we can see on the oscilloscope. So by changing the frequency, you have to find out for which range to which range output is steady state. There is no change in the frequency, it means it is in lock range. And at higher frequency, there is a change in the frequency, it means we are in the capture range. So theoretically we calculate that 2.5 nearer to 2.5 kHz there is a capture range, and from 1.5 to 3 kHz there is a lock range. So by doing these experiments, you have to find out lock range, capture range as well as frequency of oscillation. This is the next experiment as a schematic trigger as a comparator circuit. Input we are applying at inverting terminal sine wave, and non-inverting terminal we have positive feedback with R1 and R2. So here we have to compare the upper triggering point and lower triggering point with the sine wave. So if upper triggering point is smaller as compared to sine wave, output is plus reset as you can see in the waveform, and vice versa. For the lower triggering point is compared with the sine wave and output is minus reset. So whenever noise level is there, we have to apply the 2 threshold voltage as a triggering signal. We have also the hysteresis between upper and lower triggering point as you can see in the waveform with plus reset and minus reset as a output voltage. So this all circuit we are going virtually implemented on multi-sim software, and we are going to observe the output waveforms. So this is the circuit diagram where we have a OPAMP 741 we are using for experiment number 11. Input signal we are applying from the function generator as a 1 kHz and 1 volt peak to peak sine wave. This signal is at inverting terminal. Non-inverting terminal is connected with R1 and R2 as a feedback element. Power supply we are applying plus 12 and minus 12 externally as you can see. And output we have at pin number 6 on the oscilloscope. So we are using the 2 channel of oscilloscope, one for input and second for the output. R1 and R2 we have 56 kilo ohms as well as 100 ohms. So based on this value we have to calculate the upper and lower triggering point. Now we run the simulation and we can see the output is a square wave, that is plus reset and minus reset. When sine wave cross the upper triggering value, output is plus reset, and when sine wave cross the lower triggering value, output is minus reset. So this waveform is available at pin number 6 on the oscilloscope. In XY mode, we can observe the transfer characteristics, that is V in versus VO, or you call as a hysteresis characteristics, that is between upper triggering and lower triggering point. So on oscilloscope, you have to note down these two values. First, you have to calculate this value upper and lower triggering point by the mathematical formula, and later on by doing the experiment from this graph, you have to note down what is the upper and lower triggering point. So this triggering point generally used to remove the noise components in the sine wave. So that is the main application of this given trigger circuit, that converts sine wave into square wave with particular threshold voltage. Experiment where we are going to find out the operating point of this differential amplifier. So same circuit is implemented by using two transistors, as you can see, BC108 with the same value of resistor, that is 4.7K, and the RA as a 6.8K. RS we use the 100 ohms, as you can see. At present both inputs are connected with ground, and we are going to measure the first VCQ, that is collector emitter voltage. So according to the calculation, that voltage is 10 volt. By measuring that voltage by multimeter, as you can see, so multimeter is connected between collector and emitter, so that value you can see as a 10.91 on multimeter as a VCQ1. Same value if the transistor is same, that is on the second multimeter, we can observe this value as a VCQ. So that is almost nearer to that 10.28. If the ideally both transistors are same, then value is same. Practically there is slight mismatch in the transistor. So this is the first value of operating point VCQ. Now I measure the tail current or IE. So I connect the multimeter in current meter range, that is on 20 milliampere range, and I remove that branch of RE resistor. So tail current is passed through this RE resistor. So theoretically we calculate this value as a 2 milliampere. By doing the experiment we find out this value, as you can see, 2.14 milliampere. So this current is our tail current, and half of this current, that is I1 and I2 as a 1 milliampere, is passed through this Q1 and Q2. So you have to note down this operating point value in your observation table for the differential amplifier. So this is all about for the first part. This is the second part of circuit for which we have to apply the AC input signal. So as you can see, we connect the function generator at this input transistor, and second transistor we connect it with the minus VE. It means second transistor is off, there is no signal, and first transistor is on where signal is applied. So we have to measure the VC1, that is the collector output voltage of first transistor, and collector output voltage of the second transistor. So input you can see from function generator as a 0.4 volt at 1 kHz sine wave we are applying, and we see the output VC1, that is a collector of first transistor, and VC2. So output you can see on the oscilloscope. Measure the value of this output voltage VC1 and note down in observation table. And VC2, that we can connect the collector terminal with the value you can see as the transistor is in off state. So you can see the value at that point as a 0 value. So I connect the collector terminal VC2 for the oscilloscope, and you can see the output as 0 volt. So this is for the first observation in second part. Second observation, as you can see, we apply the two input signal, that is Vin1 as well as Vin2 from the second function generator, and by taking the multiple value of Vin1 and Vin2, you have to note down the output voltage Vc1 and Vc2 with respect to ground, as you can see by the green wire. So input 1 and input 2 are connected with the function generator, and output Vc1 and Vc2 we are going to observe on the oscilloscope. So by taking the value of 100 millivolt, 200 millivolt, like that, we have to check the value of output voltage on the oscilloscope. So take the multiple value and measure the Vc1 and Vc2 with respect to ground. So at present oscilloscope is connected at Vc1, and we can see the value of voltage on the oscilloscope. So note down this value on the observation table by multiplying with appropriate scale. And same time measure the VC2 also. That is on the second terminal of collector. So by taking the value of input voltage, we can measure the value of collector voltage. Now I change the value of source voltage by keeping second value of function generator same, and you have to note down again the VC1 and VC2 on the oscilloscope. So this you have to repeat for the multiple values of Vin1 and Vin2. So this is the second part of this experiment where we are applying the differential input voltage. Now in third observation we are applying the common input voltage. As you can see that both input terminals, that is the 150 millivolt from the function generator sine wave, and we have to observe the VC1 and VC2. So if the common input is there, output at both terminals, as you can see, the same value. So graph the value you can see on the oscilloscope and multiply it appropriate scale. So common mode signal or common mode gain is generally 0 ideally, but practically you have to note down this value, and then by taking the Vin1 as a 150 millivolt, Vin1 as a 0, both inputs are 0 or both inputs are 150 millivolt, we have to see the VC1 and VC2. So for common mode of signal, the output voltage is 0 or gain of the common mode is 0. Then you have to calculate the AD by ACM, that is called the common mode rejection ratio. So that value is very large because your ACM value is very small. So this is all about for the first experiment.